Okay, so have we solved this question or not? So what is this? Means what is asked in this question? For the circuit shown in the figure, the delay of NOR gates, multiplexer and inverter are 2 nanosecond, 1.5 and 1 nanosecond respectively. If all the input PQ, RST are applied at the same time, the maximum propagation delay in nanosecond of the circuit is. So you need to find what? Maximum propagation delay of this circuit. Okay, maximum propagation delay. So look over here, it is given that NOR gates have delay of 2 nanoseconds. So NOR gate has delay of 2 nanoseconds and multiplexers and inverter have 1.5 and 1 respectively. And inverter has 1 nanosecond. So here it is asked maximum propagation delay. So we should understand what do we mean by this maximum propagation delay. So by maximum propagation delay, we mean that all the gates are suffering from delay. So one very important concept I want to share with you. So look very carefully. Concept of propagation delay. Okay, concept of propagation delay. So what is this propagation delay concept? Let us discuss. Just give me a second. So look, suppose if we have a gate, an AND gate, assume that this is your ideal AND gate. Okay, that means if at t equal to 0 0, at t equal to 0 0, if input to this AND gate is 1 1, so means at t equal to 0 minus, let me assume that there was no input given, so that means this was 0 0. And if this is an ideal AND gate, so immediately when I apply the input, so output will be also generated, so output will be 1 1. But assume this AND gate is practical AND gate and it has 2 nanosecond delay. So at t equal to 0 minus, if inputs were 0 0, at t equal to 0, I apply 1 1. So after 2 nanoseconds, output will be what? It will be equal to 1. Okay, output will be equal to 1. Now assume my, still this is your practical AND gate. Assume at t equal to 0 minus, my input was 0 0 and at t equal to 0, I applied input as 0 1. So initially at 0 minus, my output was what? Output was 0 due to the fact that one of the input or more than one input of AND gate, if it is 0, output will be 0. At 0th second, you can see there has been a transition in one of the input, that is from 0 to 1, the second input. Okay, previously it was 0 0 at 0 minus, now it is 0 1. But my output is not changing. This is practical AND gate. My output is not changing. It is still 0 0. So here you are going to say that output will stabilize at t equal to 0 nanosecond only. even the fact here is that this AND gate is what? This AND gate is your non-ideal, or it has delay of 2 nanoseconds. So propagation delay is basically the delay or the time taken by the gate to stabilize the output. Okay, stabilize the output. So here you can see initially also output was 0, and when I changed one of the input, still my output is 0. So here propagation delay, it didn't come into effect. So propagation delay will only come into effect when there is a transition in states. When there is a transition in outputs, only at that time propagation delay will come into play. Did we understand this concept? The concept of propagation delay is that there should be transition in state. Here you can see previous means initially the output was 0, and even after change in your input, output is still 0. So even your propagation delay of the gate being 2 nanoseconds, there was no transition. Okay, so this is what we mean by propagation delay. Any doubt?
Yes, sir. So, yes, but we are changing our bits, right?
Yes.
Yeah, that's it. Okay, the output is 0, but there should be a propagation delay. So because we are changing the bits and also that bits going.
So what? But you tell me, if we are changing the bit, is your output making a transition? No, see, propagation delay is the time which is taken by a gate or a circuit or a sequential circuit, a combinational circuit, to basically stabilize the output. Okay, stabilize the output. So here, as your output is not making any transition, so that is why there is no concept of propagation delay. Is this clear?
Yeah, so take this case that 0 and 1 is there, right? 0 and 1, and from
for what gate?
Such same gate, like NAND gate.
Okay. So at t equal to 0 minus, you have 0 and 1. Okay.
And t equal to 0, I did like 0, 0.
Okay, you took 0, 0. So what will happen? Your output will be still 0. There will be no concept of propagation delay. Even the fact is that there is propagation delay of 2 nanoseconds. See, your output is not making any transition. But if you think at t equal to 0, if you had applied this input
1, 1, sir.
1, 1. So now this propagation delay effect will kick in. Okay, now it will kick in. Why? Due to the fact that when I apply this input, there is a transition in output state. Previously it was 0 at t equal to 0 minus. Now when I applied 1, 1 at t equal to 0, after 2 nanosecond, my output will stabilize to 1. Okay, in between this 0 and 2 nanosecond, my output will still remain at 0 only. After 2 nanosecond, my output will become 1. Is this clear?
Yes.
Okay, fine. Now come back to this question once again. So here it is asked, what will be the maximum propagation delay? Okay, maximum propagation delay. See, basically, this 2 mux is operated by this t input. Okay, you can see if t is 0, then what will happen? You can see there will be a particular path for this one. So we will be taking this path. If t is equal to 0, I am telling, okay? If t is equal to 0. So this path we will take. Okay. So let me explain this. Case 1. Case 1 is what? If t is equal to 0. So first understand, then you can solve. So if t is equal to 0, so this will be 0. Okay, t is equal to 0, and as this is passing through inverter, so this will be 1. So what will be the path of my input to output? You can see the path of input will be, as S0 is 0 in this mux 1, and let me assume this is mux 2. So in mux 1, selection line is 0, so this will be selected. Okay, so we have reached over here. Now you can see S0 is 1 over here, so that means this path is going to be selected. Now here it is asked maximum propagation delay. Maximum propagation delay means each of the element is suffering from delay. So look over here now very carefully. So it is given NOR gate has propagation delay of 2 nanoseconds. So when you apply input, so 2 nanosecond is taken over here for the output of this NOR gate to get stabilized. Now this is actually output of this NOR gate is the input of this mux. So after 2 nanosecond, this mux got input. So mux has your what? It has your propagation delay of 1.5 nanosecond. So 1.5 nanosecond. Now output of this mux is actually input of this mux. So this mux again has 1.5 nanosecond. And what about this NOT gate? So this NOT gate has 1 nanosecond. So this will be what? 2, 3, 5. So sorry, 6. Tell me, is this okay or not? 6 nanosecond. Is this okay with everyone? Tell me if this is clear or not. 6 nanosecond. Respond that you have understood or not, everyone. Jisha George. So is this your first class, Jisha? Since I haven't seen you. Okay, so everyone is telling yes, yes, yes. This is wrong. Note this down. Make a box and write this is wrong. Why this is wrong? Now see very carefully. Okay. You need to write this in your notebook so that later on you can see that where can you make mistake. So look very carefully. At t equal to 0, t means time t equal to 0. All the inputs are applied. All the input p, q, r, s, t, all the inputs are applied. See, t equal to time equal to 0. This t is 0. I am assuming. So if this is 0, after 1 nanosecond, output of this inverter has stabilized to 1. See very carefully. After 1 nanosecond, output of this inverter has stabilized to 1. But you can see output of this NOR gate is taking 2 nanoseconds. So basically, why should we consider this gate's propagation delay? Because its output has already stabilized before the stabilization of this NOR gate. So already this output, this time has been taken care from this NOR gate. So we are going to write 2 nanosecond of this NOR gate, 1.5 nanosecond of this mux, and 1.5 nanosecond of this mux. We are totally going to ignore this NOT gate due to the fact that this has already stabilized within 1 nanosecond after the application of input, whereas this NOR gate only requires 2 nanoseconds. So the time at which this is getting stabilized, this output 1 has already stabilized. So we are not going to consider this 1 nanosecond, in this calculation. So this will be what? 2 plus 3, that is 5 nanosecond when t is equal to 0. Now tell me, is this clear? Is the concept clear? Is the concept clear now? Everyone tell me why we are ignoring this 1 nanosecond. Anyone have any doubt? So you can ask. So now look, case 2. Case 2 is what? Case 2 is when t is equal to 1. When t is equal to 1. So what will be the path of input to output now? Okay, path of input to output. So you can see now, at time 0, t is 1. So after 1 nanosecond, what will happen? After 1 nanosecond, this will get stabilized to 0. Okay. Now look very carefully. This input t has been applied at time 0. So this is already present. Okay. Whatever is p, this is already present at t equal to 0, means time 0. Now for this input, when is this input ready? Okay. So you can see as you have applied one, so the path of input will be something like this. Okay, so this input of this NOR gate, it will be ready after 1 nanosecond for this and 1.5 nanosecond for this. So after 2.5 nanosecond, this input is ready. So write 1 plus 1.5, and for this NOR gate, it is 2 nanosecond. Okay, 2 nanosecond. Why? This input P is already present from t equal to 0, time t equal to 0, but this input, it required 2.5 nanosecond. Okay, it required 2.5 nanosecond to get this input. And after application of 2.5 nanosecond, basically this gate will take more 2 nanosecond to give output, and this output will be the input of the mux, and mux will require 1.5 more. So this is 1.5 more. So in total 1.5, 1.5, 3 plus 2, 5, 5 plus 1, 6. So 6 nanosecond. So here it is asked maximum propagation delay. So out of 5 and 6, 6 is maximum. So answer of this question will be 6 nanosecond. Tell me if this is clear to you or not. All of you please respond if this is clear or not. So that is why this question is very good question. Okay. Which part again, Shubham, where you haven't understood? Case 2, can you please explain?
Sir,
So look,
understood all of them, but I want you to just go through a summarized one, sir, because it's just messy. So,
yes.
yeah, sir. So just summarize it once, sir. Okay, how it's worked.
See, look. So at t equal to 1, so this is 1, this will be 0 after 1 nanosecond. After 1 nanosecond, this will be 0. But we will not be considering the effect of this gate. Why? Due to the fact that you can see when I apply t equal to 1, so what will happen? Your direction or the path of the input will be something like this. Okay. Now for getting output of this inverter, I will take 1 nanosecond. So if this is taking 1 nanosecond, already within 1 nanosecond, this has already stabilized. So the decision has been made by this mux that it needs to accept this 0th input and pass it on to the output. Okay, so within 1 nanosecond, this mux has already made the decision that it needs to pass this 0th input to your output. Okay, and you can see now, that basically this mux, now you might argue that sir, even over here if you are telling that this is 1 nanosecond, so this mux, you can see input of this mux, it is getting ready after 1 nanosecond. Okay, so after 1 nanosecond input is getting ready. Now this mux, it will produce the output after how many nanoseconds? After 1.5 nanosecond. And this output is basically input of this NOR gate. So one of the input of this NOR gate, that is P, it is present from t equal to 0. But one of another input, it is getting stabilized after 2.5 nanosecond, 1 plus 1.5. So after 2.5 nanosecond, this input is getting stabilized. So this NOR gate, it will require 2 nanoseconds more to produce output. And output of this NOR gate is basically the input of this mux. So this input will be getting stabilized at output Y after 1.5 more nanoseconds. So that is why I have basically added all of them and said 6 nanoseconds. So here it is asked maximum propagation delay. So maximum propagation delay is happening in the case of t equal to 1. So that is why my answer is 6, not 5. If they had asked over here instead of maximum, minimum propagation delay, then your answer would have been 5 nanoseconds. Is this clear? Chandana and Shubham, tell me if this is clear to you guys or not.
Hello.
Yes, Piyush.
I have a doubt. In the statement, if all the inputs PQRS and T are applied at the same time instant, if it implies that we are setting PQR and S at 1 at t equal to 0, then t should also be set from 0 to 1. Why we are discussing both cases, like t equal to 0 and t equal to 1? We should be only following t equal to 1.
What I
Like
am not getting? Pardon?
t is already 0. Before t equal to 0, time equal to 0 nanosecond, t is already 0. So why we are taking that case, like
See, you don't
that
know
as
that. You don't know that. You don't know that. For the last case, this case, I have assumed it like this. Now, there might be a case something like this also. Let us assume that t equal to 0 minus my inputs were 1, 1. At t equal to 0, okay, my inputs are now 0, 1. So you can see basically your output is making transition from 1 to 0 after 2 nanoseconds. So this can also be the case. Why are you assuming that always it will be 0? I can also assume a case like this. I can assume a case like this. Tell me. If I am wrong, then tell me. Are you getting my point? Piyush?
if there was actually a change even before time equal to 0 nanosecond, the question would have like already have mentioned about that. But here, like if there is nothing, as usual, we will be assuming that okay, at from time equal to 0 nanosecond, we will observe, we will apply all the inputs, and we will clearly observe all the changes happening in the circuit. Like is this way we should
Yes,
be
we are observing the changes. Now see, basically this T input has the highest priority because actually it is selecting the which input path will be propagated to the output. So that is why we are making different cases of T. We are making different cases of T because this T is driving the multiplexer. Okay, so that is why we are making two cases of T over here, T equal to 0 and T equal to 1, due to the fact that we don't know that initially whether the state of T is 0 or if it is 1. Here I have assumed that initially at T equal to 0 minus, my T was actually what? It was 1. Has any place it has been given that your inputs are fixed to 0 or 1? It has not been given. So that is why initially I am considering over here T is equal to 1, and at T equal to 0, time equal to 0, I am making a transition of capital T from 1 to 0. And here the opposite case, that initially capital T was 0 at T equal to 0 minus, I am making a transition to 1 along with all the inputs being changed. Now tell me if it is clear or not. Okay. So now, okay. So now we have what? We have parallel binary adders. Okay, parallel binary adder. So what do we mean by parallel binary adder? So basically, sometimes what happens, we need to add two or more than two 1-bit numbers. Sorry, means more than 1-bit numbers we want to add, two 1-bit or more than 1-bit number. Like some numbers can be, if I want to add A and B, so I can, means the number A and B can be 2-bit number. So then I will be adding like this, for example 1101 if I am adding, or it can be 4-bit number, two 4-bit number, so then it will be okay, it can be something like this. So two 4-bit number if I am adding, so some number like this. So this addition is basically done by parallel binary adder. Now there are two types of adder. Okay, one is your ripple carry adder, one is your look ahead carry adder. So look ahead carry adder, it is not required. Why? Due to the fact that it has been never asked in any of the exam, and if you want to study about it, so today actually what happened, I couldn't make the slide of that. Okay, I couldn't make the slide of that. So in the next class we are going to discuss about look ahead carry adder. Today we are going to discuss about ripple carry adder. Okay, so look what is basically happen in this ripple carry adder. Okay, let me ask you one thing. A string of 4 binary number is known as what? Something like this. What is this known as? Computer science people, they will know. So this is known as nibble. Okay, nibble. So basically we are going to add 2 nibble over here. So let us see how we add. See, this is basically the diagram of 4-bit binary parallel adder. So here you can see we have basically 4 half adder I have written. We have 4 full adders. Okay, full adder. So full adder has 3 inputs. Okay, 3 inputs. 2 of them are your bits and 1 of them is carry input. Okay, so this is your LSB position. This is your MSB position. So suppose if you add A3, A2, A1, A0 with B3, B2, B1, B0. So this is your LSB, this will be your MSB. Okay. So here when I start from LSB, there is no carry. Initially at this position I have no input carry. So you can see I have grounded it. Okay, I have grounded it. Now if this is your ideal binary parallel adder, listen very carefully now. If this is ideal binary parallel adder, what will happen? All the inputs are being applied. Okay, all the inputs are being applied, and as it is ideal, so none of the full adder suffer from delay. So immediately this Cout will be generated and it will be propagated to the next full adder. Okay, next bit it will be propagated. Immediately it will get all the 3 inputs and it will produce the sum bit and carry out will be generated. Like this, this will continue. This effect is actually what? This is your rippling effect. Rippling effect is going on. So that is why the name ripple carry adder. Okay, ripple carry adder. Now over here in this circuit, you can see that all this carry, Cout, means the carry generated at this stage. Okay, these are what? These are basically your, means even at this stage. Okay, so all the carry generated at this stage, these are your intermediate carry. You have no information of intermediate carry. Only the carry you get is Cout, which is actually the carry of this 2 bit which you get over here at this position. Okay, at this position you get the carry. This is your output, one of the output, and the remaining output are what? It is your sum bit, S3, S2, S1, S0. So the output in this ripple carry adder is what? This Cout and all the sum bit. So if I want to write, this will be your S3, S2, S1, S0. Now what I said, if this is your practical full adder, ideal full adder, there will not be any propagation delay, and the moment you apply all the inputs, you will get the output. But this is not the actual case. Okay, this is not the actual case. We have what? We have your propagation delay, a finite propagation delay in all the full adder. So what will happen? Suppose all this input A3, A2, A1, A0, B3, B2, B1, B0, it is applied at t equal to 0. Okay, t equal to 0, we apply the inputs. So after some finite time, this Cout will be generated and it will be supplied to this full adder 1, the subsequent next full adder. So let me assume that it is TPD. Okay, after TPD time. So after TPD time, if I get this C in, so what will happen? This will produce this Cout after TPD mode time. So here all the inputs are going to be present at 2 TPD. Similarly, this will produce after 1 more TPD. So input of this stage will be produced after 3 TPD. Okay, input will be We will get the input at 3 TPD stage. So, okay, so there is a finite amount of propagation delay due to this. Basically, my Cout is propagating from one stage to another stage. Tell me if this is clear or not. This propagation delay and this rippling. So until and unless this full adder cannot perform its complete operation until and unless it gets this input carry. Okay, so this we will get after a finite amount of propagation delay. Now there is some very good concepts involved over here that we are going to discuss. First tell me, have you understood this concept or not? This concept of propagation delay over here, and what do we mean by rippling over here? Have you understood this? Have we understood this or not? If you have any doubts, you can ask. Okay, so now we have a very good concept over here. Concept of some propagation delay and carry propagation delay. Okay, and then we have a concept of worst case delay. So first, let me tell you what is worst case delay. Worst case delay means in a given circuit, we have worst case delay when all the components of the circuit suffer from delay. That means what? If I have a circuit, all the outputs are making a transition. I am assuming that all the outputs are making transition. Due to that, we have maximum delay. So worst case delay means what? We mean maximum delay. Okay, maximum delay. We mean that basically maximum delay. When can we get maximum delay? We will get in a circuit when all the components are suffering from delay, or you can say all the component has transitions in the output so that they are basically suffering from delay. So tell me, have you understood the concept of worst case delay? And if you have any doubt, you can ask. So now here we have some concept of carry propagation delay and some propagation delay. So carry propagation delay means the time taken by a full adder to produce carry. Okay, time taken by the full adder to produce a carry in your ripple carry adder. And your some propagation delay means what? The time taken by a full adder to produce sum. Okay, sum means this one and carry means this one. So this is your sum propagation delay and carry propagation delay. Okay, so if you guys have any doubt, you can ask immediately. Don't feel shy. Now let us assume that in the first case, we are assuming that we have worst propagation delay. Okay, worst propagation delay. Okay, so worst case delay, or you can even say worst propagation delay. So worst case delay. So in worst case delay, we mean that all the half adders are suffering from delay. All the half adders. So let us assume some propagation delay over here is 1 nanosecond and carry propagation delay is 2 nanoseconds according to our example. And let us assume as I told you, all the gate means all the full add means again I have written half adder. So as it is worst case delay, I am assuming that all the full adders are suffering from delay. So let me take one example. Okay, so 1 0 1 0, or this is not correct. 0 1 0 1. Let me check once. So 1 plus 1 is 0, carry is 1. 0 carry is 1. 1 carry is 1 0 1. Okay, fine. So worst case delay means what? All the full adders are suffering from delay. Okay, so I have assumed that this is my input, this is A, this is B. Now look very carefully. Okay, look very carefully. These are my inputs: S0, S1, S2, S3 and C out. Okay, C out. So let me assume this is C out 1, C out 2, C out, okay, C out 0, C out 1. First understand, then I will give you time to copy. Okay, first understand. C out 1, C out 2, C out 3, and this is also C out 3. Okay, now look at t equal to 0, 0 minus. Let us assume that all the full adder were actually in your reset state. That means what? Reset state means everything was 0 0. Everything is 0 0. Okay, everything is 0 0. So if these all the bits are 0 0, then this is 0. Even this will be, this C out will be 0. And if this C out is 0, this is 0. This is also 0. This 0. This 0. This is also 0. Over here 0. Everything is 0. Okay, so I have written this using this color. Okay, this purple color, I have written this. I don't know what color is this. Maybe this is purple color. Now assume at t equal to 0, I am applying all the inputs. So here A is, all the A are 1 1 1 and B is what? 0 1 0 1. Now look very carefully. Okay, look very carefully. What is happening? I am telling you that here, oh, wait a minute. Means I will not be able to get this formula because one plus one will be 0. So here I won't be getting propagation delay. Okay, let us see. Okay, fine. We will get. Okay. No. It's okay. Let us not take any example, because if I take example, there will be problems over here. I cannot derive the formula. Okay. Means I thought I will be able to derive this using the formula, but sorry, using an example, but it's okay. So now look very carefully. Worst case delay means what? That all the full adders are suffering from delay. All the full adders are suffering from delay. At every places you are getting the effect of delay. So now look very carefully. I apply the inputs at t equal to 0. Okay, at t equal to 0 I apply. So here you can see that S0 for generating sum of any of the full adder, it will take 1 nanosecond and carry will be generated after 2 nanoseconds. So look very carefully. I have applied input A3, B3, A2, B2, A1, B1, A0, B0 at t equal to 0. So I cancelled that input because it would have been very difficult to actually show. But look here. So you can see what? that this S0 bit, it will be produced after 1 nanosecond. Why? Because I have written over here SPD, that is sum propagation delay is 1 nanosecond. So after 1 nanosecond, this output S0 is ready. But what about the C out? So C out will be ready after 2 nanoseconds. So after 2 nanoseconds, this C out will be propagated to your subsequent next full adder. So this full adder will get its complete input at t equal to 2 nanoseconds. This A1 B1 was applied at t equal to 0, but this full adder 1 was waiting for this C in to get stabilized, and it got stabilized after 2 nanoseconds. So at 2 nanoseconds we got this input. So after 1 more nanosecond, that is 2 plus 1, I will get this S1. So that is what? That is your 3 nanosecond. And after 2 more nanosecond, that is at 4 nanosecond, I will be getting C out of this full adder. So this full adder 2 will get its complete set of input at t equal to 4 nanosecond, as it was waiting for this C in to get stabilized. A2 B2 was applied at t equal to 0, but this C in was missing. So we got this at 4 nanosecond. So after 5 nanosecond, means 4 plus 1, this sum will be stabilizing, and after 6 nanosecond we will get this C out. So the complete set of input for this full adder, it will be generated at 6 nanosecond. Okay, it will be completed at 6 nanosecond. So after 1 more nanosecond, that is 7 nanosecond, S3 will be generated, and this C out will be generated after 8 nanosecond. So your complete set of input, C out, S3, S2, S1, S0, it is being generated after what? After 8 nanosecond. So whenever sum propagation delay is less than carry propagation delay, your worst case delay is what? Worst case delay is equal to N into CPD, where N is what? N is number of full adders. So here you can see it is 4. CPD is what? It is 2 nanoseconds. So this is 8 nanoseconds, which we got using the analysis of this circuit. So this is the formula of worst case delay when sum propagation delay is less than carry propagation delay. If this is clear, I want all of you to note this down very quickly. So note this down. Note this down very quickly. I am giving you like 1 minute to note this down. And if you have any doubts, you can ask. We will have one more case over here. I am giving you 1 minute. So this is very important. One of the very important questions has been asked. Completed? Okay, now see the next concept. Now assume that sum propagation delay is 2 nanosecond and carry propagation delay is 1 nanosecond. That means what? Sum propagation delay is greater than carry propagation delay. Now what will be the worst case delay? So assume at t equal to 0, I am applying all the input A3, B3, A2, B2, A1, B1, A0, B0. So after 2 nanosecond, after the application of this input, as we have applied it at t equal to 0, this sum will be generated at 2 nanosecond. But this carry, the subsequent carry, intermediate carry, it will be generated at 1 nanosecond. So your input of this full adder 1, it will be getting stabilized at 1 nanosecond because it was waiting for this scene, and this got stabilized at 1 nanosecond, and this inputs were present from t equal to 0. So after 3 nanosecond, because 1 plus 2, so that will be 3 nanosecond, this S1 will be generated. But this C out, it will be generated after 2 nanosecond. Why? At 1 nanosecond, all the inputs had stabilized. So 1 more nanosecond is required for carry propagation delay. So this will be 2 nanoseconds. So input of this full adder 2, it has stabilized at 2 nanosecond. So S2 will be getting generated at your 4 nanosecond, whereas the C out 2, it will be generated after 1 more nanosecond. So 2 plus 1, that is 3 nanosecond. So after 3 nanosecond, input of this full adder has stabilized. So C out will be generated at 4 nanosecond, but this S3, look over here. All the inputs have already been generated, S0, S1, S2, C out. It has been generated at 4 nanosecond, but this output S3, it has still not stabilized. It has still not stabilized. So what will happen? This will be getting generated after 2 more nanosecond. So 3 plus 2 is 5 nanosecond. So here your worst case propagation delay is how much? It is 5 nanosecond. So the formula, if I want to write of worst case delay, it is actually n minus 1 CPD plus SPD. Why? Because you can see in the subsequent stages up to here, everything that was mattering was this CPD, how fast CPD is getting repelled. But in the last stage, we got CPD, but we were waiting for this S3. So that is why, due to this last stage, we have one SPD added over here. So now if you do this, so n over here is 4, so 3 minus 1 into 1, carry propagation delay is 1 nanosecond. Sorry, 3 I have written. So that will be 4 minus 1, as there are 4 full adders, into 1 plus SPD is what? It is 2. So this will be 3 plus 2, that is 5 nanosecond. So after all this analysis, we are getting the same thing using this formula. So tell me if this is clear or not. Is this clear, everyone? So we have two formula. One is for when some propagation delay is less than carry propagation delay. Another is what? When some propagation delay is greater than carry propagation delay. And remember, these are your worst case delay. I have calculated the worst case delay. Worst case delay means what? That it is actually your maximum delay. Maximum delay means what? That all the full adders are suffering from delay, or all the outputs of the full adders are suffering from delay. Okay, is this clear? So note it down very quickly. Note it down quickly. Note this quickly. Now we have a very important concept, but before that we will solve one question. Okay, fine. So now we have one question. This one. Tell me what will be the answer. Answers quickly. Just now we have seen the case. It's just addition and multiplication you have to do. So any one of you have given gate this year? 2022? 195 nanoseconds you are telling, correct? Anyone? So any one of you have given gate this year? No one. Okay. So see here. Bhumika, what you want to say? Okay, you are also getting 195. So what is the question? A 16-bit triple carry adder is realized using 16 full adder as shown in the figure. The carry propagation delay of each full adder is 12 nanosecond and the sum propagation delay is 15 nanosecond. The worst case delay in nanosecond of the 16-bit adder. So it is said worst case delay. As sum propagation delay is greater than carry, your formula will be n minus 1 into CPD plus SPD. So this will be what? 16 minus 1 into 12 plus 15. So that is 15 into 12 plus 15. So 15 into 12 is 180 plus 15. So that is 195 nanosecond. So 195 nanosecond is your correct answer. Okay, 195 nanosecond is the correct answer. If we had reversed this, what if CPD was 15 and SPD was 12, then what? As S is as S is less than C, formula will be what? It will be N into CPD. So N is 16 into 15. So 15 into 15 is 225. So this will be then 240 nanoseconds. Okay, 240 nanoseconds we will get the answer for this case. Okay, 240. Yes, very good. So now we have one more very good concept. See, this type of question was asked once. Okay, I will show you the question. This question. Okay, this question. Now, why there was a problem? Okay, when I took example over here, if you remember 1111 and 1010, there was some problem over here. Why? So remember, whenever in such kind of question, if they give you input, okay, instead of giving just sum propagation delay and carry propagation delay, if they give you input bits, okay, input bits, that means you cannot apply the formula. You have to check basically in which full adder there is your delay and in which full adder there is no delay. So for that I have taken one example for you guys. So look over here and understand the concept now very carefully. Okay, this is one of the most important concept. Okay, so now see, I have such kind of input. Okay, I have such kind of input and I am applying this input at t equal to 0. So A is what? A is 1 0 1 0 and B is what? B is 0 0 1 1. I have applied this input at t equal to 0. Now I am taking just a single case over here, that sum propagation delay is 2 nanosecond and carry propagation delay is 1 nanosecond. Okay, so before writing this t equal to 0, I should have written what is at t equal to 0 minus. So everything that I am writing with green color, it corresponds to t equal to 0 minus. So at 0 minus, let us assume that all the adder, they were reset, again half adder. So I have copied the same diagram, so that is why you can see the same mistake has been repeated. Okay, so everything with green color, it corresponds to what? That it has been applied at 0 minus. So let us assume as everything was resetted, so this was everything is 0 0 0. So this sum will be 0, is this C out will be 0, this is 0, this will be 0, this C out is 0, this C in is 0, this is 0 0. Everything is 0 over here. Okay, everything is 0. So black color corresponds to everything that I have applied at t equal to 0. Now look very carefully. When I apply this input A naught equal to 0, see, A naught has not made any transition, but B naught has made transition. So if B naught has made transition, obviously any one of the following C out or this sum, it will do what? It will make a transition. So look here, some propagation delay I have assumed. Nobody is going to note. Everybody is going to understand the concept first, then you can note down the concept. First understand this, then you can note. I will give you 2-3 minutes to note it down. Okay. So look very carefully. So as there is transition in one of the input, what will happen? This sum, if you add it 0 plus 1, this will become 1, but after how many nanoseconds? After 2 nanoseconds. Why? Because some propagation delay is 2 nanoseconds, and for generating this sum, so it has changed from 0 to 1, so we will require 2 nanoseconds. But look at the C out. Initially it was 0 0. When I add 0 plus 1, there will be no generation of carry. So initially at t equal to 0 minus, this was 0, and still this is 0 minus, means this is 0 only. So that means what? This 0, it was present from 0 minus and there is no transition. So this full adder 1 has all its input present from t equal to 0 only. Okay, t equal to 0 only, all the inputs were present. So this sum, it will be generated at 2 nanosecond, not at 3 nanosecond, because this all the 3 inputs were available from t equal to 0, and this carry, it did not make any transition. At 0 minus also it was 0, at 0 plus also it is 0 only. So t equal to 0, there is no transition in the carry, and this input has been applied at t equal to 0. So all the set of input was present from t equal to 0. So this sum will be also generated at 2 nanosecond. Means you can see why 2 nanosecond. Sorry, not even 2 nanosecond. I am wrong. I am very sorry. So look, everything was present from t equal to 0. Listen very carefully. When you add 0 plus 0, it was 0. When you add 1 plus 1, it is still 0. So this output will be produced at 0 nanosecond. Why? Because output is not making any transition. Initially also it was 0. After the application of input also it is 0. So this output will be stabilized at 0 nanosecond. But look at this C out. Previously when I add 0 plus 0, there was no carry generated, it was 0. But when I add 1 plus 1, sum is 0, carry will be generated, and this carry will be generated after 1 nanosecond application of input. Input was applied at 0 nanosecond, so this carry will be generated at 1 nanosecond. So this will be transmitted over here, and this set of input, you can see it has stabilized at 1 nanosecond. It has stabilized at 1 nanosecond. But now look over here. Now there is some important concepts. At 1 nanosecond, basically, I have all the 3 inputs available with me. So sum will be generated after 2 nanoseconds. But look at this carry. See, when I add 0 plus 0 plus 1, sum will be 1, but carry will be 0, and initially carry was 0. Again carry will be 0. So this 0 is actually present from t equal to 0 nanosecond only. Okay. So all the input of this full adder, so 0, this was present from t equal to 0. Now when I add this 3, my sum will become 1. So this sum will be generated at 1 nanosecond. Why? Because all the 3 inputs were present at 1 nanosecond. And this Cout, you can see what? Even this will be what? This is also means there will be no carry generated when I add 1 plus 0 plus 0. So this Cout is 0. It is also present from t equal to 0 nanosecond. So for generating the output, that is basically what? 1, 0, 1, and this is your sum bit, and carry bit is what? Carry bit is 0. So for producing this set of output, what is the propagation delay over here? So you can see the maximum time I am taking is 2 nanosecond. So for this particular question, propagation delay will be 2 nanosecond. Tell me if this concept is clear to you guys or not. If this is not clear, I will explain it once again. Yes, tell me.
So the last one, full adder 3, you wrote here 1 nanosecond. It must be 2 nanosecond.
Yeah. So some propagation delay, yes, it will be 2 nanosecond. This will be 2 nanosecond, yes. Yes, I will be explaining it once again. 2 nanosecond. So those of you who didn't understand, try to understand this time, and those of you who have understood, once again you see. Okay. So look, I am starting it from the beginning. So assume that my sum propagation delay is 2 nanosecond, carry propagation delay is 1 nanosecond, and I have this input. Assume everything is reset before the application of input. So this input has been applied at t equal to 0. So at t equal to 0 minus, everything is 0. So with green color, I am writing all the stages, means all the output input at t equal to 0 minus. Okay. So if I add 0, 0, 0, 0, so everything is going to be 0 and it will be stabilized. Okay. So your output is what? When you add 0, 0, 0, 0, 0, 0, 0, 0. So output will be 0, 0, 0, 0 and carry out will be also 0. So all this output, so these are your outputs. These are your sum bit and this is your carry bit. Everything is stabilized at 0 minus. Now what happens? I apply the input, this 2 input at t equal to 0. So whatever I will be writing with black, that means it is corresponding to t equal to 0 or greater than 0. Now see very carefully. So at t equal to 0, what happens? I give all the inputs, okay, all the inputs I apply. So now look, one of the bit of this half adder has made a transition from 0 to 1. So obviously any one of the carry or sum is going to change. Okay, we need to check. So initially when I had added 0, 0, output of this half adder was 0. Now I have changed my input to 0, 1 of this half adder. So what will happen? Sum will be generated after 2 nanosecond. And what will be that sum? It will be 1. Okay, it will be 1 and this will be generated at 2 nanosecond. But what about the carry? See, when I had added 0 plus 0, carry is 0. When I add 0 plus 1, carry is still 0. So that means there is no transition in the output of this full adder in your carry. So this is 0. This green color 0 was present at 0 minus. This black color 0 It is at t equal to 0. Why? Because there is no transition in the carry. And I told propagation delay will only come into play when there is your transition in the output. So this C out is basically what? Output of this half adder. And there is no transition in the output, so there is no propagation delay. So that means what? This 0, it is present from t equal to 0 only. So all the input of this half adder, it is present from t equal to 0. Chandana, did you understand up to this point? Everybody tell me, have you understood up to this point? If anyone have any doubt up till this point, let me know. So now look, what happens? When you have added 0 plus 0, sum was 0 at t equal to 0 minus. When you add 1 plus 1, then also sum will be 0. So when there is no transition in output, so one of the output of this half adder is the sum bit. It is making no transition. So this output has stabilized at 0 nanosecond. But when you add 0 plus 0, there is no carry. But when you add 1 plus 1 plus 0, there will be a carry generated. Now you can see there is a transition in one of the output of this half adder one, and this one is going to be generated after how many nanosecond? See, input has been applied at t equal to 0. Carry propagation delay is 1 nanosecond. So this will be taking, means this output, C out of this half adder one, it will be getting stabilized at 1 nanosecond. So this full adder will have the complete set of input at 1 nanosecond, So look over here. When you were adding 0 plus 0, okay, 0 plus 0, carry was also 0, sum was 0. When you add 0 plus 0 plus 1, sum will be 1, okay, sum will be 1. As you have applied the input at 1 nanosecond, so this sum will be getting stabilized at 2 nanosecond. Sorry, 1 plus 2, that is 3 nanosecond. So last time I think I had made some mistake. I didn't write 3 nanosecond over here. This is 3 nanosecond. Okay, this is 3 nanosecond. So look, this sum it is getting stabilized at 3 nanosecond. But what about this carry? When you add 0 plus 0 plus 0, C out is 0. When you add 0 plus 0 plus 1, C out is still 0. So this 0 is present over here again from t equal to 0 nanosecond. So when you add 0 plus 0 plus 0, sum is 0. But when you add 1 plus 0 plus 0, sum will be 1. And this will take how many nanosecond to generate? 2 nanosecond. Why? Because all the inputs were available at t equal to 0. And when you add 1 plus 0 plus 0, C out will be how much? C out will be 0 only. And this 0 was present from 0 nanosecond and it is not making any transition. So you can see your output has stabilized all the output S3, S2, S1, S0 within 3 nanosecond. So the carry propagation delay for this question is what? Sorry, carry propagation I am telling. The propagation delay for this particular question is what? 3 nanosecond. Now tell me everyone, is this clear? So in the last case, I had made a mistake that I didn't consider 1 nanosecond over here. So that is why we were getting 2 nanoseconds over here. So now everyone, is this clear? Tell me, everyone, is this clear?
Hello.
Yes, Piyush, tell me.
Suppose if the C out 0 would have been 1 and the S, and when we are taking to
this one is 1.
C out 0, C out 0.
Okay, this one. Okay.
This one, yes. If this would have been 1, then definitely the sum 1. This one, the sum 1, yes, that one. This one would have taken 2 nanosecond extra. Suppose if the C out 0 would have been changing from 0 to 1.
Yes. So if this had changed from 0 to 1, so for generating carry we would have required 1 nanosecond. So over here we would have got 1. So all the inputs have been present from 1 nanosecond because this scene would have required 1 nanosecond to stabilize. So when we add 1 plus 1 plus 1, sum is 1, carry is also 1. So this over here, this sum would have been 1 at 2 nanosecond, and this carry would have been generated after 1 plus 1, 2 nanosecond. So this, it would have come 1 after 2 nanoseconds. So everything would have changed. Okay, everything would have changed. Tell me if this is clear or not. If this is clear, I will give you one more question to solve immediately. Okay, so note it down. First, everybody note it down. First, whatever I have written, note this down. Okay, so note this. First, note this, understand this concept. So I am pausing the video. First, understand this. Answers, anyone? Three. Okay, so you guys are getting 3. So let us check. Okay, so I need to erase it. So, okay, you guys have already noted. So what was the input? 1101 and 0011. This was the input. Can you guys tell me once? Please confirm if this was the input I have given. So still green color will correspond to everything that was present at 0 minus. 1101 and 0101. Okay, sorry. 0101. 0101. Okay. So now look. We apply this input at t equal to 0. Okay, we apply this input at t equal to 0. So this is what? 1 1 0 1, and v is what? 0 1 0 1. Okay, so now look very carefully. What is happening over here? So you can see that initially of this half, again half adder, so I had pressed actually Control Z. Okay, so that is why my mistakes are also getting repeated. So look, initially this was 0 0. Okay, so sum was 0. Now when I add 1 1, okay, at t equal to 0, sum is still 1. So sum propagation delay and carry. Sum propagation delay was 2 nanosecond, carry propagation delay was 1 nanosecond. So sum will be equal to 0 only. So the output of this full adder 0, the sum is not making any transition. So this 0 will be present at 0 nanosecond. But what about C out? So you can see when we add 0 0, okay, so carry out will be 0, but when we add 1 1, carry will be 1. So this one will be generated after 1 nanosecond, and this one is actually the input of this full adder 1. So full adder 1, you can see the inputs were initially 0 0, then at t equal to 0, a1 b1 is also 0, but cin is 1. So if cin is 1, when we add 0 0 1, sum will be 1. So this one will be generated, means all my inputs have been applied at 1 nanosecond. Okay, this one came after 1 nanosecond. So this one will be generated after 3 nanosecond. But look at this carry. when we add 0, 0, 1, no carry will be generated. So this Cout was present from t equal to 0. So output of this full means input of this full adder was present from t equal to 0. So now look, when we add 0, 0, 0, sum is 0, carry is 0. But when we add 1, 1, 0, sum is 0. So you can see again there is no transition in output. So this will be 0 nanoseconds. And when we add 1, 1, 0, carry will be 1. But for generating this carry, how much time we require? We require 1 nanosecond. So this one will be transmitted over here. And all the inputs of this full adder 3 will be present by 1 nanosecond. Okay, by 1 nanosecond. So when we add 1 plus 0 plus 1, sum will be 0. So sum will be 0. Initially also this was 0. Now also it is 0. So this will be generated at, means this is already present from 0 nanosecond. Okay, as there is no transition. But when we add 1 plus 1, so carry out will be 1 and this will be generated after 2 nanosecond. Okay, 2 nanosecond, this will change to 1. So the maximum propagation delay you can see is 3 nanosecond. So for this question, your propagation delay will be 3 nanosecond. Tell me if this is clear or not. If this is clear or not. Yes or no? Anyone having any doubts? So you can ask. Bhumika, you have something to say? Okay, fine. So if you guys have something to say, you can say. So this question, this will be your homework. So this question is based on the same concept. Only thing is that here they haven't told you sum and carry propagation delay. Here all the full adders have been broken into its respective half adders. Okay. So this is one half adder, this is another half adder, and you can see they have been combined to form a full adder. So this question will actually test your understanding, and this question I am going to solve in the next class because it will take me more than 30 to 45 minutes for solving this question. And this was one of the best question, okay, till date asked from combinational circuit. So I want you to solve this question, and in tomorrow's class, tomorrow also we have a class, we will solve this question. Okay, so this will be your homework. Here they haven't told you what will be sum and carry. Instead they have given you XOR, AND and OR gate. You need to see where all your inputs are changing such that output of the gates are transitioning in the subsequent full adders. Okay, you need to see this. See here Z0 is also 1. So input carry is also 1. So you need to check all the things and then you need to solve the question. Okay, is this thing clear? So I will send the slide, or you can just take the screenshot of this question. I will be sending the slides today only on the Google Drive and let you know in the group. But still, I will say that you take screenshot of this question. Okay. So now our next concept is what? Next concept is, we were doing actually multiplexer. So how to generate a 4x1 mux using a 2x1 mux. So look very carefully. So a 4x1 mux has 4 input. So how do we generate using 2x1 mux? So let me write this as S0 dash, okay, S0 dash, and this is S0. Okay. So now you can see what? That this is basically your, we have 4 inputs and 1 output. So can you tell me what will be the order of election line, I am telling, selection line, whether it will be S naught, means S naught dash S naught, or S naught dash. What will be the order of selection line? Means which will be MSB, which will be LSB? Option 1 or option 2, which is correct? See, basically 4 cross 1 mux has 2 selection lines, and out of the 2, one will be MSB, one will be LSB. So you need to tell me which of that, means which of the options is correct for the selection line. Tell me. See, look over here. If you take this one, okay, if you take this one, so this is your output, okay, O dash, okay. So look, combinations can be 0 1 1 0 1 1. So look very carefully. When S naught dash is 0 and S naught is 0, so S naught 0 means what? This is 0. So obviously this line will come over here and this line will come over here. And what is S naught dash? S naught dash is also 0. So that means this line will be forwarded over here. So you can see I naught is being selected, means I naught, this small I naught, okay. So this is being selected. So this I naught I1, I naught I1, these are all the inputs of your 2 cross 1 mux, and this I naught I1, I2, I3, this is the input of the combined 4 cross 1 mux, okay. So you can see I naught is being selected. So in the next case, S naught dash is 0. So this is 0 and this is 1. So when this is 1, what will happen? This input will be going over to here and this input will be going from here to here, okay. And S naught dash is 0, okay. S naught dash is still 0. So that means what? This input will be connected. So I1 is being transmitted to I naught, means O dash. So this will be what? This will be I1. Look, when it is 1 0. So when this is 1 0, so this will be 1, this will be 0, okay. So 0 means this line and this line is getting connected over here, and this is 1. So 1 means this line will be selected over here. So that means what? I2 will be selected at output. Similarly, if you put 1 1, so this will be I3, okay. This will be what? This will be I3. So always remember, the mux that is driving the maximum number of other mux, its selection line is what? It is your MSB. Or the mux that is nearest to the output, it is basically what? It is your MSB. And the mux that is farthest from the output, it is your LSB. Okay, is this clear? Tell me if this is clear or not. Is this clear? So I want you to design what? I want you to design 8 cross 1 mux using 2 cross 1. So this will not be asked in examination, but still you can do. So I will be doing it very in a shortcut way. I will be doing. If I want to design 8 cross 1 mux, so 8 cross 1 mux has 8 inputs. So even this is very large over here. See, look over here. All the selection lines will be shorted. So over here we will have inputs from I0 to I3, from here from I4 to I7, from here I8 to I11, and from here I12 to I15. In total there are 16 inputs. Okay, so these are your mux, these will be your output, and this is your selection line. So this output will be fed one by one to two more 2x1 mux. Okay, so this will be S0, this will be S1, and this will be S2. This selection line will be MSB and this will be LSB. Suppose if I want to select your 11th line, okay, sorry, 11th line I want to select. So 11 corresponds, means I had to draw 8x1 mux. Sorry, that's what I did. Means I have created 16x1 mux. I am very, very sorry. So these are all 2x1 mux. So here I will be having I0 to I1. Here I will have I0, I3. Here I will have I4, I5. Here I will have I6, I7. Okay. Suppose I want to select I5. I5 to output. So this corresponds to what? 101. So selection line 2, selection line 1, selection line 0. So selection line 0 is what? It is 1. So 1 means what? All the first line will be connected to your input. So over here this one, this one, this one, and this one. So the first line over here is fourth one. Okay. Means have I done some mistake? Yes. It says first line. So first, these are all I0, I1, I0, I1, I0, I1, I0, I1. Okay. So S0 is 1, S1 is 0, and S2 is 1. So if S0 is 1, that means all the lines, these lines will be connected to your output. Okay. So these are going to be transmitted from here. Now look, S1 is what? It is 0. So these are what? These are I0, I0, sorry, I1, I0, I1. So these all line will be now transmitted. Okay. So here it is 1. So 1 means what? This is I0, this is I1. So this line will be corresponded over here. So you can see what? This whole line is being connected to your output, and over here I1 will be connected to your I5 of the whole 8x1 mux. So that is why you can see that the mux that is your nearest to your output, that will be your MSB, and the mux that is farthest from your MSB, that will farthest from your output, that will be your LSB. So here in the subsequent stages we have selection line common. You can see over here. Tell me if this concept is clear to you guys or not. Everyone tell me. See, this will not be asked to you in GATE exam. They will ask you how to construct 8x1 mux using 2x1 mux. How many total number of 2x1 mux will be required for 8x1 mux? So you are going to say that 7, 4 plus 2 plus 1. So 7. Now if I ask you 32x1 mux has to be constructed using 2 cross 1 mux. So what is the total number of 2 cross 1 mux? Can you guys tell me? What will be the total number of 2 cross 1 mux to make a 32 cross 1 mux? 31. 31 Raju is telling. So you are coming to this like for 4 cross 1 mux we required 3, for 8 cross 1 mux we required 7, for 32 cross 1 mux we will require 31. So that is wrong concept. Okay, so 31 is the correct answer. Okay, so even means I have to check. Okay, so it's okay. It's okay. So look now. See, there is a simple technique. Repeatedly divide this by 2 because you need to construct it using 2 cross 1 mux. So 32 divided by is 2. 32 divided by 2 quotient is 16. So in the next stage divided by 2 once again. So 8 sorry, 8 divided by 2 is 4, 4 divided by 2 is 2, and 2 divided by 2 is 1. So 16 plus 8 plus 4 plus 2 plus 1. So 24, 28, 28 plus 3, 31. Now if I ask you, 32 cross 1 needs to be generated using combination of 4 cross 1 and 2 cross 1 mux such that we use minimum number of mux. So what will be your answer? Such kind of question will be also asked. See, 32 cross 1 mux has to be constructed using combination of 4 cross 1 mux and 2 cross 1 mux. What is the minimum number of mux that we will require? Chandana is telling. So look over here. 32. You need to divide this 32 with the largest available mux you have. So that is what? That is 4. So divided by 4. What you get? 8. So 8 once again you can divide it with 4. So that you will get is what? Again you got 4. Again 4 you can divide it by 4. So that will be 1. So you will be requiring 8 plus 4 plus 1. So that is 13 number of mux will be required. How come 3? Sorry, this here is 2. Means I am very sorry. So sorry. So this will be 8. 8 divided by 4 is 2. Now see, you cannot divide this 2 by 4. You need to divide this 2 by 2. So this will be 1. So 8 plus 2. This will be the number of 4 cross 1 mux and 1 2 cross 1 mux. So in total 10 4 cross 1 mux and 1 2 cross 1 mux. In total 11 mux will be required. Chandana, how you are getting 3? You won't be getting 3 over here. So 11 is the correct answer. Tell me if this is clear to you or not. Everybody clear? Any doubts, anyone? So such kind of question will be asked in your engineering services, or even in GATE exam it has been asked once or twice in your 1 mark question. Okay. So the next thing is what we have is demultiplexer. So what do we mean by demultiplexer? So a demultiplexer is basically, okay, first let me ask you, what is the motivation of multiplexer? I'm sorry, demultiplexer. See, multiplexer and demultiplexer, it is basically used to reduce your number of, or it is used to reduce the wiring. How? So you can look in this example. Suppose I have 4 stations, 4 transmitter and 4 receiver. So each of this transmitter needs to connect with receivers. Similarly, this will also connect to all the 4. Okay. Similarly, all of them. So each one of the transmitter to receiver, let us assume that 1 kilometer of wire is required. Okay, just an example. So in total, how much length of wire will be required? So there are 4 transmitter. Each of the transmitter is using 1 kilometer wire to connect with the one receiver, and there are 4 receivers. So in total, 16 kilometer of length of wire will be required. But with the help of this demultiplexer, we can reduce this very drastically. Okay, we can reduce this very drastically. Piyush, you have something to say? Yes, here we can use one mux and one demux. So this is the normal way of doing. So here we require 16 kilometer. Now assume if I have one pair of 4 cross 1 and 4 cross 1 mux and 1 cross 4 demux. So what will happen? So we had 4 transmitter over here and 4 receivers. Now with the help of this mux and demux, you can see, suppose if I want to transmit from this transmitter A to C, okay, A to receiver C over here. So this is receiver A, B, C, D, and this is transmitter A, B, C, D. So I want to transmit from A to C. So what I will be doing? I will be simply putting 0, 0 over here and 1, 0 over here. So now you can see, for connecting any one of the transmitter to the 4 receiver one at a time, I am requiring just 1 kilometer length of wire. So the basic motivation for demux and mux is that we convert a parallel to serial line to a serial to parallel line. So this is serial to parallel, one to many, and this is many to one or parallel to serial. Okay. So demux is just the opposite of multiplexer. It transmits one of the input line to your multiple output line one at a time with the help of selection lines. Okay. So simply, if I want to write the output over here, so this will be O0 will be equal to S1 S0 complement I. O1 will be S1 S0 I. O2 will be S1 S0 complement I, and O3 will be S1 S0 I. So this is what? This is the basic about demultiplexer. Okay, so we are not going to go that much in your demultiplexer because it has been not asked that much in your examination, and even if it is asked, this will be very, very simple. Okay, most of the time multiplexers are asked. Okay, so any doubt in this? Any doubt in this? Okay, can you draw the circuit diagram for this demux? Circuit diagram for the demux? Circuit diagram. It is very simple. Very simple. So first is what? O naught. So this is what? S1 complement, S naught complement, I1, sorry, I. So I is a common line. Okay. So I can keep one common line for I. I shouldn't be using this much space. So I will draw later on. Okay. First let me complete the circuit. So next is what? S1 complement S naught. So this will be the case. Second is S1 S naught complement. Last is okay. So either you can keep a common line for I, or here, because I don't want to make the diagram clumsy, I am keeping I over here. Okay, but usually there is one single line for I. So this will be O naught, this will be O1, this will be O2, this will be O3. So this is the circuit diagram for your demultiplexer. Okay, is this clear? Any doubt in this, or else we will move to next topic. So that,
So,
yes, tell me.
sir, it's S1 bar in O1 NASA. So you put like S1 S naught.
Okay, so that is S1 bar. Yes, S1 bar. Now this is okay. Okay, now this is fine. S1 bar, S naught, S1 bar, S naught. Yes, this is now okay. Okay, this is okay now. Okay, so the next topic is what? Comparator. So what do we mean by comparator? Basically, we have two 1-bit number that we want to compare. So 2-bit number can be AB. So based on the comparison, we can have three results. Okay, if we have two 1-bit number, either A can be greater than B, A can be equal to B, or A can be less than B. Okay, so these three are the options that are means output that we can get. So look over here, if we have a 1-bit comparator. So 1-bit comparator means what? A, B. The possible combination of A, B can be what? 0, 0, 0, 1, 1, 0, 1, 1. So questions have been asked from comparator. Now output can be what? Either output can be A greater than B, or output can be A equal to B, or output can be A less than B. So when this is happening 0, 0, so output is means A is equal to B, so this output will be high, remaining all others will be 0. See over here, A is less than B, so this will be high, remaining all will be 0. Here A is greater than B, so this will be high, remaining all will be 0. In the last case, again you can see A is equal to B, remaining all will be 0. Now if I want to write output of A greater than B in Boolean expression, so that will be what? A B complement, because here you can see A is 1, B is 0. So 1 corresponds to normal variable and B corresponds to 0. So that means complemented. If I want to write A equal to B, so there are two combinations when A and B both are 0. So A complement, B complement, or when A and B both are 1. So that is A dot B. So this I can write A XNOR B. And last is what? A less than B. For A less than B, we have one option, that is A equal to 0. and B equal to 1. So that is what? A complement B. So these are our result for 1-bit comparator. Tell me if this is clear to you or not. Is this clear? Is this clear? Now I will ask you one more thing. Is this clear? So now let us do for 2-bit. Okay, 2-bit. So 2 bits means what? A will look something like this, A1 A0, and B will look something like B1 B0. So Shubham, you want to ask something?
Sir, the last slide, sir, I was noting.
Okay, so now look over here. If A is equal to A1 A0, B equal to B1 B0, where A1 and B1 are MSB, and A0 and B0 are LSB. So again, now this time what will happen? I need to make combinations of A1 A0, B1 B0. So how many total combinations will be there? How many total combination? Tell me how many combinations we will have. See. So what is happening to you guys? Very good. 16 combinations will be there. Okay, 16 combination. So either A1 A0 B1 B0 will be 0 0 0, or it will be 0 0 1. So like this I can write. So anyone know the shortcut for this one? See. So now this is the long way of doing. Okay, very long way. So you can see what? A1 A0 0, B1 B0 0. So this will be 1, remaining all 0. Over here you can see B1 B0 is 0 1, A1 A0 is 0 0. So A is less than B, so this will be 1, remaining all 0. Again here A is less than B, because B1 B0 is 1 0 and A0 is still. Again over here this will be 1, remaining all 0. Now in the next case you can see 0 1 0 0. So A is greater than B. Over here you can see A is equal to B. Okay. In this case you can see B is greater than 1. So this will be 1. Over here again you can see B is greater than A. In this case A is greater than B. A is greater than B. A is equal to B. And over here B is greater than A. In the last case A is greater than B, A is greater than B, A is greater than B, and over here it is equal. So we have filled this table. Now what we need to do? For this particular case, let us make K-map and we can solve it. Okay, we can solve it. We will get equation of output A greater than B in terms of A1, A0, B1, B0. Okay, we will get a function something like this. But this is very tedious to do. We cannot do like this in examination. We have one question also. Okay, we have one question like this. Okay, we have one question like this. So now we want to solve this. So how do we do it? Look over here. Okay, so I had made the table over here. It's okay, I forgot. So look how we do this. So A greater than B, A equal to B, A less than B. So what is the shortcut trick? Okay. So A is what? A is A1 A0 and B is what? B1 B0. So first case I am writing when A is greater than B. So that means what? Either A1 is greater than B1. So then what will happen here, as these are binary number, so a1 greater than b1 means what? A1 is 1, b1 is 0. Or what can be another case? A1 equal to b1 and a naught greater than b naught. Okay. So a1 equal to b1 means what? Either it can be 0 0 or it can be 1 1. So now look how I write this in your Boolean expression. So if I want to write a1 greater than b1, so a1 can be, means a1 will be 1 and b1 will be 0. So this can be written as a b complement or corresponds to plus, and here either this will be 0 0 or 1 1. So I can write a XNOR with b and means dot a naught greater than b naught, means a naught will be 1, b naught will be 0. So this I can write a naught b naught dash. So this will be what? Output of a greater than b. Tell me if this is clear or not. Is this clear? So without even solving and doing all these things, we had written like this. Is this clear? Now next will be what? Output when a is equal to b. So this case, how can we get? So when a1 is equal to b1 and a naught is equal to b naught. Now either a1 b1 can be 0 0 or 1 1, and a naught b naught can be also 0 0 or it can be 1 1. So I can write it like a1 XNOR with b1 and corresponds to dot in Boolean, and this will be a naught XNOR with b naught. So this is the output expression for a equal to b. Similarly, we can write for a less than b. So in this case, either a1 will be less than b1 or a1 equal to b1 and a naught less than b naught. So if I want to write this in Boolean, this will be what? A1 complement b1 plus a1 XNOR b1 dot a naught complement b naught. Tell me if this is clear or not. Is this step clear to everyone? All the steps? Any doubts in this? Okay. So homework will be, you guys need to write for 4-bit comparator. So here a will be equal to a3, a2, a1, a naught, and b will be equal to b3, b2, b1, b naught. So you need to write output for a greater than b, a equal to b, and a less than b. All the 3 outputs you need to write and come in your next class. Okay. So before that, let us solve one question. So this question, tell me, what will be your answer? So solve this question very quickly. Same kind of question you can see. Sorry. So what answer are we getting? D. Okay. So look how we solve this. Here it is given, let x1, x0, y1, y0 be unsigned 2-bit number. Means they are normal number, not in complemented form. The function f is equal to 1 when x is greater than 1 and f is equal to 0 otherwise. So here you need to find if this number corresponds to x and this corresponds to y, you need to find the output expression for x greater than y. So either x1 will be greater than y1 or x1 equal to y1 and x0 greater than y0. So this will be what? X1 dot y1 complement plus x1 y1 x0 and x0 y0 complement. So which option do we see? So here you can see none of the options are matching. Okay, none of the options are matching due to the fact that all these options are minimized, but this is not minimized expression. Okay, this is not minimized expression. If you open this, this will be what? x1 y1 x0 y0 plus x1 y1 x0 y0 complement, and then again you need to rearrange it like this. x1 x0 y1 y0 plus x1 complement x0 y1 complement y0 complement, and then you need to form K-map and solve, but it is not required. You can see why. See, this min term, this is already minimized. Okay, this is minimized and you can see it is available only in one of the options, that is option D. So a smart student will never do minimization of this by drawing K-map. You can observe over here that this min term, it is already minimized. This cannot be minimized anymore and it is present over here, because if this term was minimized, so in a basically this is what? This is a 4 variable K-map. In a 4 variable K-map, when do we get a min term that has 2 variables, something like this, x1 y1? For which group? How many group of 1 we get a variable, means min term like this? How many group of 1? See, if it is a 4 variable, so we will get a group of 3 when we have, means we will get 3 variables, something like this, x1, x0, y1, or even x1 bar, x0, y1, when we have group of 2 ones, 2 ones, okay, we will have x1, x0 or x1, y1 like this when we have group of 4 ones. We will have single variable like x1, y1, x1 complement when we have group of 8. So here you can see if there was group of 8 in the options, so there would have been a single variable. So that means this term, as there is no single variable, that means this is already minimized. So this should be present in the option, and you can see only in one option, option D, this is present. In rest of the options, you can see there is a, means there are 3 variables present. That means there are 2 group of 2 present. So option D is your correct answer even without solving. Tell me, have you understood this concept or not? Did we understand this concept? Yes or no? Is this clear? If anyone have any doubt, you can ask. So all we have left is with decoder and encoder. So this we will finish in next class. Okay. In next class we are going to finish this. In today's session we will end over here. Okay. So tell me, have you understood this concept? Means this question, what I told you, without even solving you can mark option D. Is this clear to you guys or not? Okay, then we will end the session over here.